About a year ago or so, I made a video about a tool that I had written called Mosplot, and this tool was supposed to be a free and open source tool that can be used to make lookup tables of MOSFET parameters that can then be used to make plots to be used in the GMOV design methodology. So since last time I have made some improvements to the code, and it's now much more flexible in the sense that you can there's probably very little possibility that you might have a situation where it's not possible to generate a lookup table. I'm not going to discuss much about how you can generate a lookup table or how you can make plots, all the sorts of things, because I think you can just read this documentation. It's perfectly straightforward to know what exactly how exactly it works. So the original goal of this tool was to have the possibility of generating plots such as this one, and then using these plots, let's say, to design an analog circuit such as an operational amplifier, such as a current mirror, and so on and so forth. So how exactly would we go about doing it? Probably you would say, okay, if you're using the GMOV design methodology, I mean, it's well known exactly how you would go about doing this. You would say, okay, I want to bias my device, let's say in the weak inversion, strong inversion, or whatever, and I'm going to decide to, based on, let's say, my gain specifications, I have the need to use this length, and based on this length and this GMOV ID, you will say, okay, this is the point here. Then you will read the ID over W, and then you will then, let's say, based on the bias current that you're using, you can get the width of your device, and then this way you have optimized that device. Nice. So the thing is, after a while, obviously, every once in a while, let's say you want to design a new amplifier, and then probably you've forgotten the design procedure, probably you can't remember anything, or maybe you still haven't forgotten anything yet, or whatever. But simply speaking, like looking at charts like this, and then making decisions like, okay, this is 15, it goes like this, and it comes here, I have to write this number down, and then you have to do the computations and calculations. I mean, even though it's nice and it whatever, it just takes a lot of time, let's say, to have one circuit. I mean, to have one circuit to meet a particular specification. If specification, for some reason, you decide that, okay, my specification was not exactly, I did not exactly have the right specifications, maybe I need a slightly a different, let's say, slew rate or whatever, suddenly you have to go through the whole process again. Then I just said, okay, if I'm able to design, if I'm able to look at this picture here, if I know this set of steps that it takes me to design an operational amplifier, and I'm doing it by inspection, like looking at this plot and all of these sort of things, obviously it's possible, let's say, to write a script that is able to that is able to automate the process for you. So which is exactly what I have done, and it's the goal of this video, is to show you that given a lookup table, basically it's almost trivial, let's say, to write a script to optimize an analog circuit. If you know how to design the analog circuit by hand, let's say manually, which is what we have been doing, like you look at this, then to automate the process is actually a very, very, very trivial process. So I'm going to give an example here so that I can show you how it's done in this how it's done in the tool now, so that maybe if you have a desire to design new types of circuits, you can probably use this tool to do that. So just to give you an example, one of the most common, let's say, simple circuits that most of us probably use is, okay, I need to use an op amp here, and then the most let's say common form of op amp, if you don't have, let's say, huge gain or whatever, is this 5T OTA. It looks like this. We have the input pair, you have the load, and then you have the tail current source, and so on and so forth. And then somebody would give you a specification, let's say it should have this particular speed, it should have this gain, and so on and so forth. So basically, let's say how do we get these equations? You come, for example, you have so many different books. You probably have this book by Allen and Holberg, and then you can come here, for example, it tells you exactly how the specifications relate to the parameters of the design. So you have these guys, tells you that the gain is going to be given by GM1 or out, and the bandwidth, and the input common mode range, and the slew rate, and so on and so forth. So you have lots of textbooks. You just open one textbook, they tell you exactly how you can design these amplifiers. Then you have your stuff. Like for example, my GBW is going to be like GM all over 2 pi CL. Then you take into account the capacitance here and the capacitance here, you add them here so that things are a little bit more accurate. And then for the design, for the GM over ID design methodology, you just convert these things into the GM over ID design, let's say variables that you use. So you divide this by ID, and then because you're dividing by ID, you have to also multiply by ID. So then just, then this guy will be your GM over ID, and then this will be your current that you're biasing at, and then this will be, let's say, the parameters of the stuff, simple stuff. So you just, the only thing that is required is you know how to compute the specifications. And to know how to compute the specifications, many textbooks, just as I showed you just now, again, the gain, this is how you compute the gain, GM R out, and R out is equal to the parallel resistance of this guy and this guy, which is like this. Again, you convert it into the GM over ID form like this. It's very simple stuff. Then for the input common mode range low, you basically say I'm at this node, how would you perform KVL to ground? And for the input common mode, the high one, you do to VDD, you get them V in low, V in high, and so on and so forth. Then for the common mode rejection ratio, it's the ratio of the differential gain over the common mode gain, and then you end up with something like this. So you have these equations. Fine. So now I'm going to show you how you can then use that how you can then let's say write the script that the tool can then, the setup that you need to have so that the tool can then, let's say, just do the rest for you. So here I'm going to show you, this is 5T OTA. So this is the guy. So for the 5T OTA, let me first of all do this. So this is, let's say, this is just the definition. So obviously you have to tell the tool where it's going to, which lookup table to use, and then what's the VDD, and what's your CL, and then what is the range of voltages that you can use for the PMOS transistors, and then what type of transistors, let's say, you want to use. Is it the low voltage or the high voltage or whatever, depending on what you have saved in the lookup table. And then you pass in all of these things into the circuit. The circuit is basically this circuit here, but I'm still not yet showing you, let's say, how the circuit is built. But for now, we have this circuit, we give it the lookup table, we tell it what the ranges are, and then what's the PMOS to use, and this, and VDD and CL. Very good. Then we have to specify what are the parameters that the tool can play with to optimize the circuit. So in the GM over ID design methodology, the two main parameters are the length and the GM over ID. So here we specify, remember, so we have these guys here. These guys are the input PMOS pair. So both of them have to be matched. So they have the same L and the same GM over ID. Same for these and same for these. So in total we have, let's say, three sets of transistors. So this is one set, and then this is another set, and this is another set. So we will specify that, okay, for the input pair, scan the range from 100 nano to 2 micro, for example. Then these are the GM over ID values, the range of GM over ID to use. So since this is an input pair, you probably want to make a large GM over ID so that it can, let's say, give you a big gain or something like that. Then for this other guy, also the load, same thing. You define the L to scan and the GM over ID to scan, similar to the tail. Then for the bias current is how much current do you want the tool, let's say, to what is the range of current that you believe, this is something that obviously if you're going to be designing something, you know, for example, that, okay, in this design, I don't want to be using more than this amount of current. So you know that, roughly speaking, my current is going to be, let's say, between 1 to 40 micro. Of course, you can make the range as big as you want. It doesn't, it probably helps the tool if the range is smaller to able to, let's say, pinpoint, because it's a smaller range to search. So anyway, this is basically just how you specify the parameters that the tool can then use, let's say, to optimize the circuit. Then we have to define the specs. So this is the specs where you specify, okay, what are the stuff that you care about. I care about the gain bandwidth. I would like it, let's say, to be about 5 5 megahertz. Then you specify that I want to maximize it, and then what's the weight in relation to the other parameters. We say 5. I mean, here I'm just basically, this is just an example. You can put whatever you feel like is more important to you. Then the gain. So here I'm saying that I want a gain of, let's say, 30 gain of 30 dB. So this is the dB, since I'm just converting it into the normal number, not in decibels. Then my I bias, I say, okay, even though I have specified here that my I bias is supposed, it can search for me from this range to this range, but if it would be nice if it can use no more than 20 micro for the I bias, which is basically the bias here, this guy. Then similarly for the slew rate, I say 5 megahertz. Now this is a how do you call it? This is a device which is not supposed to be using lots of current. So if you want a very fast slew rate, probably this is I mean, you will be expending a lot of current. So it depends on how much you let's say how much current you want to burn. Then you have your input command mode range, and now since this is an input, so since the input pair is a PMOS, it can go very low, so you can, let's say, go as close, very close to ground. And then for the high, probably not, it can't go very high, but you know, again, why not just say, try your best. Then you say, I'm just specifying here to maximize, something like that. Then CMRR, it's the common mode rejection ratio. Here we have specified that the gain is supposed to be about 30 dB. So the common mode rejection ratio, which is the ratio of the common mode gain over the how do you call it? No, the ratio of the differential gain over the common mode. This is the differential gain. This is the ratio of the differential gain over the common mode gain. So we want to say that it's 70 dB. I mean, that's a lot. Maybe it might not even get it, but anyway. So this is the area. Also, we would like to optimize, let's say, the area. Don't get me a huge device. So here you can see that I specified that I want a device of 5 pico. 5 micrometer square, let's say, if it's possible, but I don't really, it doesn't matter if it violates it, if it's not able, let's say, to get me 5, it doesn't matter. So something around 5 is okay. Anyway, so again, we have specified the parameters and the target, and then here we just tell the optimizer, okay, what's the circuit? Again, we have not yet, let's say, I've not shown you yet the circuit, but the circuit exists. And then what are the parameters? Of course, these are the parameters that we have here, and then the target spec, and that's it. And then you tell the optimizer, optimize, then how many iterations, let's say, you want it to do, and then after that we just print out, let's say, the results of the optimization, so that we can know, we can get the stuff. So now we have an idea of, basically, you define a circuit, you define the parameters that the optimizer uses, and then the specs that the optimizer uses, let's say, to move closer to what you want. Now, I'm going to discuss now the circuit. How do we let's say, how do we write the circuit part? Now, as I said, the only thing that we have to do is these things. I mean, these are the most important part. If you have these things, then probably the process is trivial. So let's go now into the circuit, and then we can see. So basically, this is a circuit. As you can see, we say that this is just the standard stuff. We do all of these sorts of things. And then, as I said just now, we have to specify how we are going to be reading information from the table. So, as I said, I'm not going to actually discuss a lot about how you can use this tool, all these sorts of things. I mean, it's obvious if you read this part that you, first of all, after you have saved the table, you have to create a MOSFET object, and then that you can then use to this. This is actually trivial stuff, so I'm not going to waste too much time on this. So anyway, we specify that. So let me just show you one last thing. So you see that we have two branches here. So usually when you have this table, you have 4 free variables that the table was built by sweeping 4 variables. You sweep the length, you sweep the gate to source voltage, drain to source voltage, and the body to source voltage, or something like that. So when you want to actually read from the table, you always have to specify 2 parameters. So you always have to specify fixed 2 parameters, while the other 2 can be ranges. So for example, you see here that here for the VGS, I'm using the full range, which is like from the full, let's say, 0 to 1.2, whereas for the VBS, I'm saying that, okay, don't consider body effect here. And VDS, I'm specifying the VDS at this particular VDS. So when it comes to, obviously, to MOSFETs, we know that VGS is the most, is let's say, it's more important, let's say, than VDS, because this is the voltage that specifies the current, whereas VDS can actually have an effect depending on that, but it's not that important. So this is why I'm fixing here, let's say, VDS and VDS. I mean, this is standard stuff. It sounds right now that I'm saying something important, but actually it's not. It's really just like standard stuff. Then so the question now you might be asking is VDS, why is it 3? As I said here, we have each branch has 3 transistors. So it's safe to assume that, let's say, the VDD is going to be divided, let's say, into it's going to be equally partitioned, let's say, into 1 1 1. So obviously, because the VDS is not a very strong voltage, this is not the, let's say, a catastrophic assumption to make. So you just make this assumption here. Probably, I would say, this is the only part of the optimization process where you have to make some decision about, like what to do. Because this may or may not, let's say, change the accuracy of the result. So as I said, we specify here that this voltage is going to be divided into 3. Okay, excellent. So 3. And now, after this, we specify then just that from the specifications that we get, for example, the PMOS input, it's the name of the PMOS input so that it can be later used. What's the name of the PMOS input and what the length, and the length that it should, the range of length that it should scan, the range of GM of ID that it should scan, which is exactly as given here. That we just, let's say, receiving them, let's say, from the outside. That's it. So very simple. Now this part is just, let's say, to compute for me the width after the device has been, let's say, after you have selected your GM over ID and your L, you probably want to know the width. So this is the function which is basically computing that. This is, let's say, standard stuff. Now the important part, which is really this is all of this so far is basically just setting things up, and it's probably going to be the same for almost all other designs. I probably will have to abstract this part at some point, let's say, in some, so that the user probably doesn't have to, let's say, do all of these sorts of things. But for now, since this functionality of optimization, all of these sorts of things were added not so long ago, I probably have not yet come to the conclusion about what to leave to the user to write and what can be abstracted away. So for now, this is fine for now. But the most important part, which is the part where the design actually is going to be, let's say, defined, is where you say evaluate specs. So this is the evaluate specs. And as I said, the parameters that we're going to receive are those parameters that we have specified down, which is the L and the GM over ID that we want to, let's say, tune, that we want to find. So we don't know the L, we don't know the GM of ID. We are asking the optimizer that, okay, these are the parameters, find them for me. So the optimizer will give them to you. So we just say, what's my L of the input and the GM of ID of the input, and so on and so forth. And then here is where you some knowledge of, let's say, you need some knowledge of analog design. It's not like you absolutely don't need any knowledge and then anything can work. You just definitely need. And where do you get all this knowledge? As I said, you open textbooks and they tell you that, okay, obviously we know that if this current is going to be, if these guys and these guys have the same W over L, then this current is going to be mirrored here, and then it's going to be split equally if these two guys are matched equally, and so on and so forth. So just like that, we come here, we put this, we say that, okay, the currents of the, you remember this guy, we say that each transistor has a name, it has a length, and it has a GM of ID, and it has a current. This is, let's say, the third variable, which we don't need to specify, but has to be specified. So you can think of these things as these things actually specify, let's say, the bias point of each transistor, the length, the GM of ID, and the current. So again, at this point, we specified that the optimizer itself is going to say, okay, I'm going to guess. I don't know. This is I bias. So you say, okay, very good. This I bias, I'm going to take it, I'm going to assign it to this transistor, and this other guys, we know that half of it is going to flow into the load, and the input we put half. So here is where now you actually have to use, just 1 second, you see all of these parameters. So let's say to compute GBW, you will have to specify that it needs the use of GM, it needs the use of CL, CDD, and this one needs the use of RDS, all these sorts of things. Of course, these are the sort of stuff that you get from the table directly. This is why you need the table, because you need to extract these parameters. So as I said just now, that we had created these things here, this part here. We say that this is a PMOS. So this is what is going to be used, let's say, to look up the parameters from the table. So now all we need to do is that we specify the name of the parameter. So each transistor, what parameters do we need from each transistor? So we come back to this, remember this guy. So for example, like this transistor, what parameters do we need? Maybe we need, obviously we need the GM of this guy. We need, let's say, the VGS of this guy, or VSG. We need the VDSAT, and so on and so forth, based on these specifications. So if one of the specifications requires the use of one of the parameters here, you basically just say, okay, this is the PMOS. This is a PMOS, and then we specify that, okay, given the current assumption for the length of this device, which is here, given the current assumption for the GM over ID of this device, please tell me what is the CDD of this device. Remember, the CDD, we need it because it's part of the GBW here. So what's this? What's the CDD? What's the VSG? What's the VDSAT? What's the GDS ID? The GDS ID is what you're going to be needing to compute, let's say, the the gain. So we get all of these things for this device. We save them here. We do the same, let's say, for the NMOS load, this guy, the NMOS load, and then after that we do the same for this guy here. So this part of the part, you see the transistor parameters, this is where we use the table to extract all of these guys. This is actually like trivial to do. As soon as you have this set of equations, you know exactly the parameters that you need, and then you just do them here. Then after we have gotten all of these parameters, all we need to do now is just write the specifications again. So you see that we say now the GBW. How do you compute the GBW? Again, just remember these equations here. GM, it's GM over ID multiplied by, you see, GM over ID multiplied by the current, which is the current, GM over ID multiplied by the current, divided by 2 pi CL this blah blah blah, divided by 2 pi CL CDD input, CDD load, and then the gain, it's GM over ID divided, this one here, you see, GM over ID divided by GDS ID plus GDS ID, the other one, and so on and so forth. ICMR, from this equation, you just write it as exactly as it is, CMRR, the slew rate, and then we compute the area since we want to optimize for the area. If you don't need to optimize for the area, you don't need to have this thing. Again, this is the guy which tells you, remember, for the area I told you. So the area will tell you that, okay, this is the length, this is the GM of ID, this is the current. Remember, as soon as you have specified the length, the GM of ID, the current, everything else, let's say, is just a computed value. So we say now, given the length, given the GM of ID, how do you compute the width? You get the current density, which is IDW, then you divide. So the current density is ID over W. So if you divide ID divided by ID over W, the W goes at the top, at the numerator, and then you just have the width. And then since we had already, let's say, computed the length, we know the width, and then we have the device dimension. So this is just, let's say, to report to us after the optimization is complete, what is the length, the width, the area, current, and GM of ID. And then, just like this, basically that's it. And then we return these things. Of course, these things will go now into the optimizer. The optimizer, as I said, will suggest a set of parameters. Not here. It's a set of parameters, which are the length, GM of ID, blah blah blah. And then we tell it basically, given those parameters that you had offered me, these are the specs. So then the optimizer will look, do the computed specs match the specs that were required by the user? Yes, it means that I'm done. Thank you very much. It prints out the result. No, yeah, it tries better, it tries more. And that's basically it. So I'm just going to run one example now just to show you how it works. We can see now this is the GB. So So this is, let's say, a set of parameters that I had set. I can probably do change some few things, but now I'm going to run one example so that we see just exactly how these things work in real time. So here I have, I'm inside here, you can see I'm print CA, I can go 5T I do LS. Here I have this design PMOS input pair, because why not? So I can do something like this. I can say design PMOS input pair, then I press enter. Now I press enter, the optimization process is going to start. The initial slowness is because it's loading the table, and it's a huge table, so like I don't know, probably 500 megabytes or something like that, so it takes a bit of time. So in about 12 seconds, probably 3 or 4 seconds of that were for loading the table. It did the 20 or 30 steps of differential evolution optimization method. So differential evolution. So basically, what I decided to go for right now is to explore the design in order to have some global optimization, which means that you can search the design space. So you have local optimization and global optimization. Local optimization means that the optimization tool can get trapped in a local minima, whereas global optimization means that it searches the whole space in almost a random manner, and then it finds one good local spot where we might have the solution, and then using that, and then from that good, let's say, spot, we can then narrow in down with a local optimization like this one. I mean, this is just like unnecessary details, I'm just telling you, but just so that you know that the tool itself is actually, I mean, obviously I didn't implement all of these things. I'm using SciPy, which has all of these things, and it's trivial, let's say, to just switch to different algorithm, but I'm just trying to explain that the one that I decided to go for now is differential evolution. And basically it's a global optimization first, and followed by local optimization, which increases the likelihood of finding a very good solution. Anyway, so as I said, because I had already abstracted, let's say, the optimization part of the code and the design report part of the code. So basically the user does not have to implement, to think about how to implement the optimizer or how to report the results. These are taken care of by default. So as long as you respect the fact that the optimizer requires, I mean, you pass in the correct stuff, which are, let's say, the circuit parameters and target specs, and you write them according as they are exactly like this. Then the tool will print out at the end of the day for you that each transistor, like PMOS input, you see, so it says that the PMOS input pair choose a length of 400 for the width, blah blah blah. This is the area of this guy, and this was the current that was used to bias it, and this is the GM of ID of this stage. Same for the load, same for the PMOS, and then it tells me what is the final circuit specs. So the GBW, I had specified that please choose for me, give me 5 megahertz, and then it computed something like 4.85, and again I specified that 30 dB. This is 30 dB, mind you, but this is 30 in terms of raw numbers. So it turns out that 30 dB and a gain of 30 are roughly almost exactly the same, which is a little bit confusing. And then the I bias, I say don't use more than what's this, 20, and then whatever. I mean, you get the thing, you get the idea now. So these are, let's say, initially I had said that the area don't use more than 5. It decided that for whatever reason that it's going to use something close to, let's say, 9 micrometer square, and so on and so forth. So I mean, just to, let's say, tell you, yeah, most of the time, I mean, you can just change the specs and then it will, let's say, do something for you that you want. So now you might be asking, okay, fine, you have just shown that. Maybe let me run another one while I'm talking. You might be saying that, well, we have these results, but are they accurate? Are they like, I mean, sure, but can you maybe prove? I mean, obviously they are accurate, let's say relatively accurate compared to, let's say, what you might do by hand. So I'm just going to show you one example right now where I'm doing this. I'm going to go to Spectre here. I have, let's say, this part here. I'm going to show you. So this is a 1T, this is the one. So I have, this is a schematic of it right now. So I'm going to actually take these values that I had just computed just now, paste them here. Okay, I already pasted them. So this is my input pair. Of course, I can automate this process also, let's say, to test and all these sorts of things, but you know, it's not that difficult, let's say, to do them right now on the video and then show you exactly what's going on. So these are the input pairs. I'm going to, let's say, just copy paste these values here that I have. So this was from a previous test that I had done just to make sure that the code is working. And then I can show you like 385. You know, it actually, since these values are not, let's say, the most accurate values in the world, so it doesn't really matter if we, let's say, put in, let's say, something slightly different or whatever. So this is the other one. Surprisingly, not very different, it seems. It seems that the tool is always seems to be finding almost a similar solution for this particular spec. Obviously, probably it's good because it means that it's consistent. Now let me just change the PMOS pair. Let's see what it had decided to go for this time. 454, whatever. I'm just going to copy paste. And then for this guy, 3.52. Seems like almost the same, you know, 3.52. Oh, 3.52. That's not correct, actually. That's 3.52. That's okay. I think I did a mistake here. Just 1 second. 3.52 micro. Is this correct? 455. Yeah, 3.52 micro. That's it. I think that's correct. So for the current, it says that we should bias this stage with 17.43. 17.43. I'm just going to use 17.5. I mean, it's not that important that I am super accurate right now. So with this in mind, now let's take this now and then. So this is a test bench. So I'm going to open one test bench and then do some of this test. So here is the part which I probably have to tell you something, is that testing an analog, testing an operational amplifier is surprisingly not as trivial as you might think. Like you might see a specific, because of to test the open loop characteristics of the op amp, because obviously for the high gain and all sorts of things you have to be very careful. So let me just show you quickly. Let me go back to this. I opened it. So this is the one. I'm going to open the design here so we can see, so that I show you the design that I'm using, let's say, for the AC test. So one more time, I think I probably just needed to save the file, and yeah, let's go back to the design here. Let's say so this is the design that I'm using, let's say, to test the open loop characteristic of, to test the AC characteristics of the op amp. As you might imagine, it's a bit I'm going to let you, let's say, you can read this book exactly, and it has a section which tells you exactly how you can test op amps, and the way you test the op amp actually can have a very strong impact on the result that you get. So what I'm using here probably is the sort of method that you might use to test your op amp in practice. There might be other methods that you can use to test the op amp that might give you more accurate results compared to what you expect, let's say, from calculations. But these are not methods that probably you can use in practice to test the op amp. So here I'm using a method which is probably practical to test. So this is why I just want to point out that there is an impact on the test bench that you use to test the AC or the open loop characteristic of the op amp. So just keep that at the back of your mind. So this is, let's say, the circuit that I'm using. This is to measure the AC part of the circuit, the AC open loop gain. Know what I'm talking about. This is to measure the differential gain. As you can see here, I'm passing in the differential gain, and this is the one which is using to measure the common mode gain. And then in the code, I will just divide the whole thing together. So I'm going to close this for now. Let me open Maestro again. So inside Maestro, all of my tests are loading. I'm going to come here, for example. I'm going to do my open loop test, which is this part here. And then here, as I said, let's open this tool to remind ourselves what we have as our specs. Maybe I can minimize this slightly so that we can see the rest of this stuff. Here now I can then run this simulation once. So here I'm running an AC test and a DC test so that we can compute all these sorts of things. So here we see these are the specs that were computed by the tool. And then we see that, for example, the first stage, we wanted to have an 8.71 micro. We got 8.47. and the second stage, not second stage, but the tail, we were supposed to give it 17.43. It got almost 17. And then the gain, the differential gain, we got something like 29.3 to 29. And then for this GBW, we got something, we are supposed to have something like 4.9, we have 4.6. Again, as I'm telling you, different ways of testing this can actually give a different result. So I might use, let's say, an ideal way of testing it, and the GBW will definitely go up, but I'm sticking to this way of testing it right now because this is the more practical version of things. So just as you can see, like with Bear, we have some very close results. And as I was telling you, the tool here is actually using interpolation, and which means that and it's using fast interpolation so that the optimization process can go quickly. So getting this close, let's say, to the result, like 29 or 4.6, and phase margin. I mean, who cares right now for the phase margin? But it's nice to know. Let's say. Now let's go to see other things. We can see, for example, the input common mode range. So basically, this is probably not the best way to test the input common mode range. Usually, of course, if you look at this book again, as I was telling you, they show you one method of testing the input common mode range, where they say that you will have to look at where the V in and V out are in linear region or something like that. But I mean, this is probably easier for me to do here. The problem what is wrong with this method? So basically, this method is checking which region the transistors are in. If the transistors are in saturation, so the input common mode range will be defined in the range where all the transistors are in saturation. The problem is this region here is something which is it's not a well-defined parameter. This is something that is not, let's say, part of the model itself. This is something that Cadence itself or Spectre is estimating. And different simulators will have different ways of, let's say, computing the region, if they have a way of computing the region. So this is for sure not let's say the proper way, let's say, to test this, but just to show you what we see. So here I'm going to show the plot clearly. So this is a plot, as we can see here. We have M1, M2, M3, and blah blah blah, and then so we can see 2 means saturation. So we see that for example, this is the M2, the load, whatever. So you can see that clearly from this region to this region, we have our how do you call it? We have our input common mode range. So this is where all of the devices are in saturation. Clearly, we see that we start at 1.144 milli, and then we have our 600. So let's see what the tool decided to give us. It said that it says that we can go as low as almost 0.13, which is I would say slightly lower than what we slightly lower than what we got, but then it says that we can go all the way to, so I mean, this is just basically splitting hairs at this point now, because I mean, if you really want to go to if you really care about 0.1 difference, probably if you take into account what's going to happen later after layout and process variation, all these sorts of things, yeah, I mean, just not worth it, let's say, to worry about these sorts of things. And then one final thing is, I mean, slew test. Who cares about slew test? Because anyway, just let me just show you quickly how it looks like. So this is the slew rate. As you can see, we have 2 types. Actually, I am not optimizing for both of them. So you have the charging slew rate. Probably I should show you maybe how it looks like, and just so that you can see. So a slew rate just basically means that you ramp up, you pass in square wave into the op amp, and then you see how quickly the output, let's say, rises, and then the slew rate, you measure it by something like this. Let me zoom in. For example, this is the rising slew rate, so which means that how long it's going to take, let's say, to charge the output capacitance or whatever capacitance that let's say is supposed to be charged. So clearly you can see, for example, from this point, let's say, to whatever it takes to the output value. And then you can measure, this is like 2.3 megavolts per second or something like that. Then we can close this, and then we can go to the other one, which tells you the other one. So you see this one and this one. This is the discharging. We have something like 3.66, which I believe is 3.46 or something like that. So you get the idea. So this one. So you can probably add another specification, let's say, to optimize for both of them. if you know the correct equation. Again, this is where you have to open a book, or maybe somewhere else, somebody else has written somewhere, you know how to optimize for that. So again, so finally, and this is, let's say, probably just to prove that, yes, the sort of stuff that we get, the sort of results that we get actually are not far from the reported specs. And one final thing, of course, so right now, as I was mentioning, this is a tool that I'm writing for myself to help me to avoid, let's say, having to constantly waste time in optimizing circuits. And so I absolutely would love to have a. So right now, let me just go. So I have tests, you can see here. So I have designs. So I have two designs that I've currently, let's say, written down. So this is the design which you can see, which is the one I just showed you, which is the design for a 5T OTA. And then this other design, I have this other design for the Miller OTA. So the Miller OTA is the two-stage one where you have to do all of these, let's say, compensation, all this nonsense. But it follows the same idea. So again, just as before, you map the transistors. You're going to have, let's say two stages. This is stage one, stage two, and then you do the same steps as before. Evaluate steps. You assign the currents, and then you start computing the parameters as required by the specs. Again, the parameters as required by the specs in stage two, and then you see from you have a book like this which tells you exactly what are the specs. How do you compute the GBW? How do you compute the DC gain? Where was I? How do you compute the CMRR, slew rate, phase margin, total current, and all these sorts of things. So maybe if you want, I just do one so that you can see LS. Let's go back. Say Miller OTA, LS. So maybe I can come here one more time and show you. Let's say, for example, here. So here is where I have the specs. I have also almost, let's say, similar specs that Is this the Miller OTA one? Yes. So again, these are the specs, and then these are the parameters. As you can see, we have a different, let's say, compensation capacitance, all these sorts of things. So we can just run one of these here to do. So Python, I think I think it has the same name. Then we can see. Again, it takes a bit of time to load the lookup table, and after that we go through the same process. It's probably slightly slower here because of obviously it's a bit of it's a larger circuit. And another thing, I probably don't need to use to go to 30 or 40, probably 5 or 6. It's very, very good enough, let's say, to give you the result. Again, so these are the results that we have. So it tells you the PMOS input, what are the sort of stuff that you need, and then finally the GBW 18 mega, the gain about. So this is a much larger gain. The bias for stage 1, bias for stage 2, common mode input range, the CMRR, phase margin, slew rate, and so on. So you see, this is a much larger slew rate because the current here is much larger. And then this was the area that it was it found for me, something like 29. So just to wrap up, as I said, right now I currently have only 2 designs that you can use, let's say, with any technology basically. So right now, if you are using this thing with who knows, TSMC 180 nanometer, TSMC 65 nanometer, whatever, all you have to do is probably just change your lookup table that you already have, and then you specify what was your VDD and what CL and what the ranges of voltages are. And then obviously you might think change maybe some of these things like what you expect is possible from the technology or not, and then you just run the script, and the script will immediately spit out for you the stuff that you need, let's say, for 5T OTA or Miller OTA. So yeah, so basically what I obviously would continue to add more scripts, let's say, to optimize other types of, let's say, circuits. Let's say, for example, if somebody wants to do a folded cascode or one of these fancy stuff that we use a lot, these basic building blocks that we constantly, let's say, have to reuse in analog design. So as soon as probably I have them, I'll probably be including them here. But I hope if somebody who is obviously watching this video, I mean, seems or somehow find this a good idea. This is an open source project, and if somebody, let's say at the moment, let's say he decides that I want full dead cascade or whatever that's not already included here, and thinks that the process that I have just described is straightforward enough, which I believe it is, and then he can maybe look at one of these books and then sees what are the steps, just implement them, test that the result that you are getting, that the specifications that you wrote are correct, test them with, let's say, with something like cadence, all these sorts of things, and then you can do a pull request, and I'll be happy, let's say, to add this into the repository, and hopefully in time we might end up having, let's say, a huge set of examples, a huge set of scripts that can be used, let's say, to optimize any sort of analog circuit for obviously any technology. And then nobody has to waste time anymore, let's say, to design an op-amp anymore. Suddenly, those professors who give you, let's say, a project to design a low noise amplifier, suddenly they have to think about something else. It's no longer like it's a trivial process, let's say, to a Miller OTA. Who cares? Like I don't want to spend the rest of my life like doing the same step over and over again. So this is, let's say, my ultimate goal is we somehow people end up people end up finding this project useful, and they somehow decide that we might want to, let's say, contribute and add, let's say, designs, useful designs that we can have, and in the long run, who knows, we might actually have something quite useful. So for now, I guess this is all I wanted to say. Bye.